Hello, good day. This video's for CE5361. I apologize for the sudden changes on Tuesday of this week, February 29th, 27th, 2024, and for the coming week. I'm committed to support some additional classes. One of them is CE4330, which is the team design class. Perhaps some of you were in it when you were undergraduates here. It's going to conflict 8 times. This is the first of the 4. I knew about this, and for some reason I space cadetted, never gotten around to tell you all or organize the schedule appropriately. So it's going to conflict 8 times. This is the first batch. There'll be another batch near the end of the semester, but we should be in good shape at that time. I'm going to make a series of these short videos to help keep the class moving along. Each video itself will be functionally fairly short, and it's mostly a software issue on my end. I'm doing this on a very archaic hardware that I put together myself 10 or 15 years ago. So it still works, it just has limits, and if the videos get too long being much over 20-25 minutes, it clobbers all my disk space and takes an eternity to upload to the mighty YouTube. I will explore also uploading directly to the media site. I think that's possible. I'll have to do a little bit of reading about that. So these next few videos are going to cover the unit hydrograph portion of our class, and any writing I have to do, I'll do on this device. It looks like that's going to be big enough, and I think I'll have ability to electronically save what I write. So enjoy the video right now that also happens to be our experimental notes. Now, bear with me, I'm going to mess with your screen a little bit. I've done this before. There's a way I can get these to work side by side, and it looks like that is the way. I got that straightened up pretty good. I should probably magic marker that on my desk somehow. This magic marker. You know, all those years working at Mad River Woodworks finally pays off. Okay, so here's where we will take notes. And so the next few meetings we're going to discuss catchment scale, runoff mechanisms. Actually, runoff. We won't use the word mechanisms. It's essentially chapter 12 of Bruce, God, how do you spell it? Name. Bruce Saert's book, B-R-U-T-S-A-E-R-T. And I've given you an assignment, exercise set 2, and I'm actually going to work solutions in these videos because that as an assignment is a very valuable explanatory introduction to the idea of catchment scale runoff. So first, let's go take a look at our textbook, chapter 12, because there is a page that I want to point out to you. So on the video, I click that doodle, move over here, click that one. Our class is not in the list, but it's easy enough to modify. Done. And readings. This is, I really didn't want it to download it, but it's a computer. It does what it wants. So this is an electronic copy of our textbook. I do not think it's the current edition. I think this is quite a bit older. I got this off the mighty internet, I think from a Taiwanese website, because there was a time in history when Taiwan did not choose to comply with international copyright laws, and so a lot of books got republished in Taiwan, and nowadays they're essentially available for the looking. Now, how that plays in U.S. copyright code, I don't know, but it gives us a tool to discuss. I think I'm rambling now. Oh, and recorded too, so excellent. What happens if I click on the plus doodle? I think that's good enough. So, Chapter 12, the title is Streamflow Response at the Catchment Scale, and Section 12.1 is the unit hydrograph. And it's this chapter and the other readings that I have laid out for you go more or less into some of the thinking aspects behind the unit hydrograph. Let me push this aside, and actually I'm not So the exercise set 2 I left for you all on the blackboard is this one right here. Apparently I got the year wrong. It should say spring 2024. And the first problem is to read a series of readings. I suggest you do them in chronological order so that you get the historical perspective of the unit hydrograph. Your actual exercise is to prepare a short synthesis essay, page or two, which synthesizes what you've read, not summarizes, but ties all the ideas together. You do want to identify the key points, common themes, and so forth. If there's different methodologies, compare and contrast. More importantly, you are teaching yourself a way to construct unit hydrographs. And then problems 2 and 3 are application of what you learn. Let's first go take a look at Sherman's paper. So this is circa 1930. So in the 1930s, people were just as smart as they are now, if not smarter. But nobody held your hand. We didn't have an internet. There was no clicking green button or no easy button. You would have to read documents like this, rework the examples as best you can until you can convince yourself that you understand or have a technique to apply whatever you are researching. So in this case, it's by L.K. Sherman. His friend Peabody and him worked on the Wayback Machine. I think Sherman was the dog in that cartoon. And the key features is the author claims and demonstrates that from a single observed hydrograph caused by a storm of known behavior, it's possible to compute the behavior of the watershed to future storms. Basically, in our context, we have the following, although we're going to lose our, we don't actually have color in this particular. There's our watershed that I've drawn ad nauseum. Tributaries, outlet. So what Sherman's paper claims is that from known rain going in, losses, oh glare is pretty awful here. That's about the best I can do for the glare. Let me try one other trick. That changes the aspect ratio too much. Going to have to live with the glare. We have losses, which in our case up to this point have been infiltration. A variety of models of that: green amped, initial abstraction constant loss, Horton's method, etc. And we actually did discuss proportional rainfall, which we're going to use in the example shortly. So infiltration and evapotranspiration go home. And those were our main losses. And then we have, we did at least address the possibility that some water stays on the watershed in depression storage and interception. I'm guessing since that doesn't make a difference, put this back where it was. There we go. Oh, I moved this. My bad. Let's see, my fans are running. How much time have I been at this? Okay, we're still at 11 minutes. I got about 3 minutes to go, and then I'll start another video. And then what comes out is that's P for precipitation. Q comes out. Our precipitation signal blocks like that. Our Q signal is our formal hydrograph. And to get from here to here, there is these various transformations, and what's called the unit hydrograph is a transfer function that takes this rainfall input after the losses have been counted for it. So conventionally, we'll go to the next page, the rainfall input, immediately what can become lost gets lost, and what's left over was called the excess precipitation, and that's what remanifests itself from wherever it falls to the outlet as the outlet hydrograph. So operationally, our approach looks something like this: time, rainfall. I'm going to draw it in big blocks because it's easier to see. Okay, maybe that's our rainfall time series. The width of these in and of itself isn't particularly important, but in what I'm drawing here, we'll assume they all have the same width. So that's a time interval, and the height of them represents a depth of rainfall uniformly distributed over our watershed. Then it goes through our loss mechanism. I'm going to use proportional losses because it's easiest to do when you're drawing this on a mighty video. Same time scale. Excess precipitation. Guess I'll call it P sub E. So if we look at that first one, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. So our first one was roughly that high. Let's suppose, for the sake of this discussion, that only half of the rain that comes in appears as runoff. The other half is lost by whatever mechanism. Evapotranspiration, infiltration, somebody wasn't paying attention to where it was. It's just lost. So this block is the excess for that portion. And if we go to the next block, it would be there, but we lose half of it. So that's its excess. We go to the next block. It would be there, but we lose half of it, which puts us about here. Go to our final block. Would be that, but we lose half. So now the shaded area, that's our excess precipitation signal. This is what can become stream flow. Good. Copy that. Switch back to marks a lot. Move to the new page. Okay, so copied and paste, there's the picture we have. So we've gone from raw rain into our excess precipitation, and now this is transformed, and the choice of the words not arbitrary. That is the conventional terminology used in most professional software packages, is a transform function or a transfer function or a linear, whatever it was in those notes, and it transforms to our outlet. So this is at the outlet as a hydrograph. Notice I've switched to the letter Q here because we've got to mind our P's and Q's, and I'm going to arbitrarily draw what the hydrograph would look like, but I will try to preserve some actually that's not right. We would expect there to be a time delay in the hydrograph, so let's be C. Maybe it looks something like that. Now the key thing is ignore these dots that I'm disappearing. Now you don't have to ignore them, they're gone. So perhaps that is our hydrograph at the outlet. The area under this curve is total volume that left the watershed. The area under this curve is the total depth that came into it. If you multiply it by the area of the watershed, that equals the total volume. So this excess precipitation signal multiplied by the watershed area produces a volume. That volume should be the same as the total volume observed at the outlet. And we leverage that requirement as a way of performing the analysis. And in analysis, our goal is, what's this function? Not what does it do, but what does it mathematically look like? So that's the conceptual essence of what's going on in unit hydrographs. Now Sherman's original paper, which this is attributed to the beginning of unit hydrograph concept, surely he had learned of it somewhere else. This can't possibly be the first one, but it's the first one that's recognized in the literature. And what he started with was triangular responses to uniform rainfall. And here we can see, just like I've drawn, the vertical pulses and then the associated hydrograph as a function of those pulses. And then the remainder of his paper goes on to present an example. So they have observed runoff, and in his case it was all runoff caused by rainfalls that were known to last for a single day. And it goes on and has another couple of examples. And this is a fairly important table because this is where it's never explicitly stated in this paper, but what's going on here is something called discrete convolution. And so each of these rainfall pulses causes its own little teeny hydrograph, and those hydrographs are added up together to produce the observed runoff hydrograph. So that's what you get out of Sherman's paper, and you get to the end, you notice there's no easy button, there's no actual procedure written in algorithmic functions. So if you had to implement this using just Sherman's paper, you could do it, but it would be a bit of an ordeal at first. The next paper I have requested that you read and summarize is, not that one, go 30 some odd years to 1964, and Dr. Lienhardt was a gentleman I used to have lunch with once a week for 17 years. He was at University of Houston at the time I knew him. Had determined that the unit hydrograph as we know it can actually be not derived so much as extracted from concepts of statistical mechanical behavior. So he goes ahead and lists a method on how to do it, and the key thing is that the hydrograph functions at the time appeared to approximate Maxwell-Boltzmann speed distributions, and he leveraged that information to construct what unit hydrographs functionally might look like. You have to read all this for your homework, so I'm not going to read it to you per se, but some of the key things to notice is there's this idea of time intervals, delta t, just like I'd drawn in my notes. And in his case, it was raindrop number, which can be converted into what we know as a depth. You assume all the raindrops are roughly the same size. You know what the count is. Count times volume over a unit area gives you depth. So it's the same information, although this is listed as number. The reason it's listed as number is the Boltzmann statistics are worked out for number distributions, not floating point random variable distributions. Then it goes on to explain the logic and the counting technique, and we'll know that this, if we look at that, that looks like a maximum likelihood functional relationship. Continues on, notices that we need to invoke the law of large numbers. They chose Stirling's approximation to factorials because factorials appear in the denominator of the end function. Key message of that is factorials implies convolution. And going on, we get close to the end, and this is instrumental in that the number ratio, time is raised to some power, but it's in the denominator. It's raised to the same power elsewhere, and then we have a decaying exponential component, and here it repeats itself. So we have a numerator portion, which is time raised to a power times a decaying exponential divided by the sum of all the prior times. So this is clearly discrete convolution at this point. And then he goes ahead and presents an example for a watershed in Illinois and the requisite arithmetic that carries along with it, and I'll leave that for you to read on your own. When we get to the end, somewhere he's got a graph. These are his watersheds, and this is his observed values plotted as step functions, and his predicted hydrograph based entirely on Boltzmann's statistics and a couple of assumptions about watershed shape. So when we get to the end, his distribution function looks like equation 19 of his paper, and we can convert that into more conventional form, which is a hydrograph functional type form, where usually it's a discharge over some peak value. And if we go back to our distributional theory, that peak value is at the measure of central tendency. And I think that's about as far as we can get out of his paper. So again, you'll have to read it on your own. Ignore these marginal notes. Those are my notes from quite a while back, and without having access to what's in my head, they probably don't have much meaning for you. But the key thing is he provides us a path to what the mathematical functional forms of unit hydrographs should look like. And what I find the key thing is these are probability distributions, hence the unit hydrograph shares the same features that a probability distribution does. On the range of minus infinity to infinity, it needs to integrate to 1. And well, that's the big one. And the values of each of the individual weights can't get larger than 1, again, because of its need to integrate to 1. And those, along with the structural relationships of the distribution, gives us some guidance on, again, what the final functional form is going to look like. So that's Lienhardt's paper. You'll all have to read that and proceed on your own. And then a few years later, it's basically the same paper, quite a bit shorter. He goes on to a somewhat more usable form of the hydrograph, and then talks about estimating the different moments involved, and those in turn are how we determine what the hydrograph shape would look like. And so at this time, this is 72, they were trying to use simple descriptions of a watershed to parameterize a unit hydrograph. What we're doing right now, short term, is we're going to use actual data and essentially fit an equation like this. So we're going to force the betas, n's, and the TRM beta to make the best fit of observations. The next major step that was not accomplished at the time was how do we turn other metrics of a watershed, slope, area, land use, land cover, time of year for all we know, mean annual precipitation, to find values of those betas, n's, TRM beta directly in the absence of complete input-output data. Here he has his hydrographs for fan-shaped and long slender. For what it's worth, we'll find out that the exponent on the pre-multiplier is what changes due to shape. And on real watersheds, real data, sometimes these numbers are quite a bit larger than 2. I mean, 9s, 10s. So his original conjecture that shape played a role was correct in the sense that it affected the exponent on these first numbers. The decay term, it also changes the exponent on the time ratio. So it's not quite as simple as implied here in this 1972 paper, but this was a major step forward in watershed hydrology, ignored by your current author, I might add. You can, well, you get to that later. Next, in roughly the same time as Lienhardt's paper, a visiting scholar from, I think, Ireland, named JCI is not his name. I have a mistake in the citation there. Was visiting the United States, 75 to 98. And during his visit, he gave a series of lectures, and this document that you are asked to read a small portion of is the result of those lectures. And the lecture 4 is the one that you're asked to read for this exercise, and it goes through the unit hydrograph concepts. Let's see, page 84. Looks like it's off by one page. That's 6, reporting is 7, so 84 should be 85. Lied to me. Stupid machine. Well, not bad. Okay, so you want to read this particular chapter. I think it's called Lesson 4. Yeah, Lesson 4. Read the entire chapter. It has some nice pictures and words, not a whole lot of arithmetic, so it should be well accessible to any of us. And goes on to describe the concept of distance from an outlet, contributing area, and time of travel. And then starts to construct unit hydrograph concepts as per actually Sherman's original paper. And has some intellectual models of the responses under different conditions, and slowly starts to get around to what the mathematical structure of a transfer function would look like. And then goes through complex storms, and again, read that, summarize it as well as you can. You'll use elements of this for doing the remainder of the exercise. Okay, I'm hitting about 35 minutes, so I'm going to stop this video, render it, and we'll pick up here. The next thing we're going to look at is Chow, Mabit, and Mays. That will be very instrumental in helping you build your own unit hydrograph analysis for problems 2 and 3 of this homework.